Hello, everyone. My name is Khalef. I am a PhD student at INSA Lyon and LaMCoS Lab. I am a member of the tribology team, and it is my pleasure today to present you my work during my first year of thesis that revolves around friction prediction from SCM images using AI. So my presentation plan is as follows. We'll begin with some basic context on friction and tribology. Then we will see our data acquisition methods, then proceed to explain the model that we have used, see some results that we have got, and finish up with some discussion and conclusion. Okay, first up, what is tribology? Well, the term was first officially introduced in 1966 by Peter Jost. It comes from the Greek word tribos, which means to rub. It is the multidisciplinary science of study of friction, lubrication, and wear. It examines how surfaces interact when they are rubbed against each other, considering different parameters such as temperature and environment. Friction, on the other hand, is the force opposing relative motion. While it is not a fundamental force, but it is present in our daily lives, such as the phenomena you're seeing here on the screen. Second, why do we predict friction, and why do we interest in studying it as tribologists? Well, for many reasons. One of them is that it is an indicator of performance. For instance, having high friction values accelerates wear and heat generation, while low friction values reduces stability and control. Other reasons can be seen here in the graph, where we have significant values of energy loss, amount of money spent, and CO2 emissions. So understanding or better understanding friction could help us reduce these numbers and improve our system's efficiency and lifespan. Okay, so the following diagram is what we call a tribological triplet. It is a conceptual model proposed by Maurice Godet and Yves Berthier. It states that friction is not an intrinsic property, but rather a system property, which means that for the same material pair, you could have a different friction coefficients depending on varying when you vary systems. Sorry about that. Okay, so it consists of three main components. The first bodies, these are the two solid surfaces in contact. The second body, which is the mechanism that connects the first bodies and imposes relative motion. And the third body, this is the most crucial and often underlooked component. It is the material that accumulates and forms in the contact surface. It can be made of wear debris, lubricants, or environmental contaminants. Okay, so this is a standard pin-on-disc test that we have done in the lab. On the left, we have a schematic representation. This is the actual setup that we have used, where a standard pin is pressed against a rotating disc with a constant normal force. During the test, we have kept some parameters fixed, such as tangential velocity, normal force, and temperature, while other parameters were varied. Specifically, atmosphere, we've used two atmospheres, air and argon, and we've changed track radius and sliding distance. We have measured a few parameters, such as tangential force, by extension the friction coefficient, because we have used a model where we calculated based on the ratio between tangential force and normal force, acceleration alongside the three axes, and we have used a coordinate system, theta, to track the wear track in the disk. Okay, so from our pin-on-disc tests, we obtained what we call this friction mapping. Here we can see that friction varies depending both on the lap number and the angular position theta. Now, the main observation here is that it is not constant. It fluctuates heavily depending both on the angular position and the lap number. And here we can see some regions that exhibit high friction values. This is most likely due to localized local parameters and third body effect. So the main question here is that why is it for the same material pair we have such a wide range of friction values? So to answer this question, we're using AI. So our idea is to have a model that takes SEM images as an input and outputs an instantaneous friction coefficient. The problem is that most AI models behave like a black box, which means you have your input and you have your output, but you do not know why your prediction is made. And for tribologists, understanding why we have such a prediction is as important as having a low prediction error. So to address this limitation, we're inspiring from a model that was first introduced in 2019 in Duke University. It's called a proto-PNet. Now, this is a predictive model that gives you your prediction or output while highlighting the region that indicated that motivated that prediction. So, for example, here in the original paper, they built a classifier for bird species, and after each prediction, you can have a small bounding box here indicating while that prediction was made. So our motivation here is to build a similar model that can draw small bounding boxes in the SEM images after a prediction is made, so we can investigate those small areas and see whether we have any cues for that prediction. Okay, so to build an AI model, we would obviously need a data set. So for each disk in the test, we have taken 3 images using 2 different detectors, a secondary electron detector and the backscatter electron detector with compositional information and topography information. We have taken images each 15 degrees in the disk. So for each disk, we have 24 values or 24 images with a total of 11 disks. Now, obviously, this is not enough to train an AI model, specifically a deep learning model. So we wanted to augment the data set a little bit more without applying any data transformation or manipulation. So what we did is that we extracted small sub-images from the original image with an overlap of 10%. The sub-images have a dimension of 224 by 224. Now, why we chose this specific dimension, we will see this answer shortly afterwards. So this operation helped us augment the current data set by a factor of 16. So we've started with 264, I think, images, up to 4,224 images. So this is not bad. So the schematic representation of the model that we are using here is quite similar to the original one. We have 3 main parts: the CNN backbone, the prototype layer, and the linear regressor. We have replaced the original classifier by a linear regressor since we are trying to predict a single value. Starting off with the first part, the convolutional backbone. Now, convolution is an operation that aims to extract information from the input image while reducing the dimensionality. This is done by sliding a small kernel, or called a filter, across the entire image. So it captures the necessary information. Some kernels, for example, capture edges or rounded shapes, different filters that capture different characteristics. So by the end of this operation, we obtain what we call a feature map. So from a simple RGB image, we have this feature map here, where F is the spatial dimension reduced, and C here is the depth of our image. This is the number of features or characteristics extracted from a single image. And it is made up of blocks. Each single block here is called a patch. As for why we used why we cropped the sub images before, because we're using a CNN backbone called ResNet-18 with the pre-trained model, pre-trained weight. I'm sorry. That takes this particular dimension as an input and outputs a feature map of size of 512 by 7 by 7. So this means that it tracks 512 features from each input image. Okay, so the next part of the model, this is the prototype layer, and this is the core idea of the model. Here we introduce a set of learnable prototypes that are updated after training. So we are working in the feature space now. We initialize a number of prototypes K, and we measure the resemblance of each prototype here with each patch in the feature map. Now, the metric we're using to quantify this resemblance is Euclidean distance. So we measure the Euclidean distance between each prototype and each patch in the feature map. So by the end, we would have been calculated the distance between each prototype in the prototype set and every single patch in the training image. And right afterwards, we take the minimal distance for each prototype, given that the smaller the distance is, the higher the resemblance between that prototype and a single region in the training set. We obtain this minimal distances tensor. We transform it into what we call a similarity score via a simple logarithmic function. And then we feed it into our linear regressor. So the inputs of our linear regressor are the similarity scores of the prototypes, and then we have our final decision making. This outputs the coefficient of friction. So the first two parts, the CNN backbone and the prototype layer, acts as a feature, act as an information extraction step. Then the final decision is made in the linear regressor part. Okay, now moving on to results. With the first set of images are the secondary electrons. Now we have two different plots here. The plot on the left is the plot for the entire sub-image dataset, and the one on the right is the averaged one. The reason why we have an averaged one is because when we crop the images before, we assign the same friction coefficient to all of the sub-images. This is not necessarily true. So in order to mitigate this effect, we average by image. We average the entire value by a single image. Okay. So we have two metrics of performance here. We have the coefficient of determination, which is 0.64, and the mean absolute error, which is around 10%. Here we see that the model does capture the trend or some morphological cues that allows to predict coefficient of friction in relatively a good way. However, in some regions, particularly this one, we do observe that the model tends to overestimate, and here it tends to underestimate the values. This is because we have an imbalance in the training data, because we had too many points here and very few points here and here. So this is probably why it predicts like this. The second set of images are the compositional mode. Now this is a slightly an improved performance here in the R2 score and the absolute error. This is around 9%. One thing to note as well is that when we divided the train and test data set, we made sure that the angles in the train set are not present in the test set. This is to test the robustness of our model. So we see here is a slightly improved performance. The third and final set of images there is for the BSE topo mode as well. So we have the best R2 score yet, and a very close mean absolute error, which is around 8%. We still notice the same behavior around this area and this area. This is mostly, if you like, to the same reason I mentioned Okay. Okay, so here we have a test image. This is the original one, and these are the sub-images extracted from the original. We computed the friction. We computed the prediction for each one. Here we have an average. I don't know if you can see it, but the actual friction value is 0.6420, and the average prediction is 0.614. So this is a really close average prediction. However, for some sub-images, we do notice that the model underestimate the friction value, and for some other sub-images, it overestimated them. This is due to this highlights the problem that I've stated earlier, that we have assigned the same friction coefficient to every subset, which is not necessarily true. As for the bounding boxes here, these corresponds to the most activated regions with the prototype. And for the heat map, here we see the hot zones here. They are plotted with, they are like the sum of the weighted contribution of each prototype in the linear regressor. So in this region here, we have the sum of the similarity score multiplied by the weight in the linear regressor. So the higher the weight or the importance of a certain prototype, the more important the region becomes. To conclude, we can say that the first results are encouraging. We are definitely continuing on this matter. We see that the importance of the data size as well. So having a bigger data size would help the performance of the model. So currently we're working on acquiring more SEM images and focusing on explaining the model's prediction via prototypes. Thank you very much for your attention, and that you have.
Thank you very much. Any questions? I'm part of the supervising team, so I cannot ask questions. I rely entirely on you.
So I try to come up with a question. So can you do this type of approach with any pair of material or objects that go through friction? Like, can you do between, for example, metal and a biological sample, like prosthetics and a joint, cartilage or something like that?
Yeah. Well, the initial setup was used. The pin on disc are made of the same metal. They're stainless steel, but I imagine that it could work for any given data set, provided that you have images and targets to predict. So technically, you could have any type of image data set with their labeled targets, and the model would train, I think, normally. So yeah, it should work.
Other questions? Yeah.
Thank you for your presentation. Given that your model helps with the interruptibility of the results, which helps for tribology field, does your proposed model have any drawback in terms of performance or metrics or maybe training time or inference?
I'm sorry, could you repeat? I didn't hear it.
I said, given the interruptibility that your model adds to the, let's say, the results.
Yes.
Does this add any drawbacks to the model? Maybe some takes time for the inference or takes more time for the training. Maybe the metrics is affected.
For the training time, it does take some time, and specifically considering that that we have used a relatively small data set, especially for deep learning tasks. So having much bigger data sets will take a bit more time. This is for sure, and a bit more computational power. But yeah, I don't know I don't know what other metrics we could use to evaluate this this model. So
Yeah.
oh. Of yeah. Do we? Well, so far, I did train a basic CNN to predict the same output, and the accuracy remains the same. So using this type of model did not impact very much the accuracy. I would also like to note that one of my supervisors already worked with a machine learning model. It was a random forest, and obtained relatively the same accuracy. So this particular approach did not impact our results. Does not mean that it will not impact any type of results. So it might or it might not, depending on both the data sets. So I cannot say for sure, but even if it does, I think it's worth it to sacrifice a little bit of accuracy to obtain interpretability. This is at least for physicists. So yeah, we're not just looking for better results. We're looking to understand why. Because for now, we're not working on an industrial project or anything. So we kind of have the liberty to explore new fields. So this is why we are taking this approach.
Yeah. I see. Thank you for your answer. And by the way, you have asked him a much better question that I had.
A few years of experience, right? Any other questions, maybe? Okay, thank you very much again. And we are now welcoming